Another very important component, op-amp, is something that we would like to have in our library toolkit so that you can use it for simulation. We will discuss now how to make a generic spice model for an op-amp and then link it up with a symbol, just like we did for the diode. So the op-amp symbol is like that. It's like a triangle and it has 5 terminals. It has 2 input terminals. One is the non-inverting terminal and the other is the inverting terminal, the one with the minus here. There are 2 power supply terminals. One is the positive power supply, another is the negative power supply, and then you have the output terminal. This is the V0. So the positive power supply is VCC, negative power supply is VEE, and this is V0. I'll call this one as V minus, and this is V plus. So these are the 5 terminals, and let me give a name for this generic component, and that is the name which is op-amp. So what are the steps? First, I need to have a model for this in a sub-circuit, just like we did for the diode with the snubber, power diode. And after we have created a model, then we have to create a symbol in KiCad. And then we link the symbol and the model. Then we have in our library a component, a generic op-amp customized component which can be used for any circuit, schematic and simulation. So let us do that. First, sub-circuit. So the sub-circuit, then name of the component is, I will say, op-amp. And all these terminals. So if I say this is terminal 1, non-inverting, terminal 2, inverting, terminal 3, positive power supply, terminal 4, negative power supply, 5 is output V0. So I can say these are the nodes, node 1, node 2, node 3, node 4, node 5. I can have a comment line above to indicate this is V plus input, this is V minus input, VCC, positive power supply node, VEE, negative power supply terminal, and V0 is the output terminal. So this is the sub-circuit definition line. Now comes the sub-circuit. What do we write here as the netlist within the sub-circuit? So the op-amp function is like that. You have V plus minus V minus. So that will be the error. So let's say plus and minus, V plus and V minus. The error V error is amplified by an internal gain, very high gain. So it is not just only a pure gain which is having a very high value for all frequency ranges. It is having a very high gain value at lower frequency ranges. At high frequencies, generally there is a tapering off of the gain, like a low pass filter. A close approximation would also be a PI controller, where a PI controller has a gain of almost infinity towards DC because of the I part, and then the gain starts tapering off. It is also something like a low pass filter. So the proposal is that I will use a PI controller type of a filter here for acting as the gain. So this will give infinite gain at lower frequency and DC. Then this is followed by a limiter, in the sense that whatever the output comes, it is limited by the power supply values. Whatever be the output, if it exceeds VCC, it will be clamped to VCC, or if it goes below VEE, it will be clamped to VEE. So then you have the V0 here. So this is the structure of the op-amp inside from a kind of a behavioral perspective. So we would like to incorporate this model into a sub-circuit. So how do we do that? So that is what we intend to do. This will give you a good generic model of an op-amp. So first let me say that in the sub-circuit I will have this one. A B source in ngSpice, it's a very powerful component element in Spice. So you can look into the ngSpice documentation. B source, it is a programmable source. It can act as both a current source or a voltage source with the value programmable. So it is a very powerful component, can be used for several purposes, and here for designing this op-amp model we will use this B source. BV error, so for this one is nothing but between two nodes. Let me say the node is ERR and 0. Between ERR and 0 I want to have this error. It will give you a voltage output which is equal to this minus this. So this value of voltage minus this. So V plus is nothing but node 1 which is passed as an input parameter. V minus is nothing but node 2 which is passed as the input parameter. And therefore the equation is V of 1 node 1 minus V of node 2. And then if I have another virtual current source, BIC current source between these two nodes, 0 and NIC, again two virtual nodes, where this B source now acts as a current source, and therefore I say I equal to, the current value is equal to, current value is proportional to or equal to VERR, which is the voltage across this node, NERR. So this current, so if I look at it, this is a current source and the current source is taking the value from VERR. So I have a current which is directly proportional to the error voltage. And I am going to feed it to a capacitance. I is proportional to VERR and the voltage across the capacitance is 1 by say integral of I dt, and I being proportional to VERR, the voltage across this is proportional to VERR. So this is the integral of the error that you see. So this is the I part. So that's what I want to incorporate. So I will say C, let's say this is the CC or the C control, NIC and 0 between these two same terminals of this in a proper direction, and let's say 1 microfarad. So this is nothing but the I part of the PI control. Now let me take the proportional part. Another B source, the current, same current between two nodes. I have I which is again proportional to V error. Same. And that current flows through a resistance to give me, the resistance is acting like a gain, Kp into error. So between these two I am having some resistance I 1 e to the power of 6, and this is the P part. This is the P part. So the voltage across this node VNIR would be the current that is flowing through this R, because that is also connected between the same two nodes, and that current is proportional to the error into the R value. So it is equivalent to Kp into error. This is equivalent to Ki into error. Now I need to add them up, right? So let me have a gain between some two nodes Nij and 0, gain of 10, let us say, for example, and I will have another B source between two nodes, and the output is the voltage, and that voltage is VNIC, which is the voltage across the capacitance, which is the integral output, into the gain, which is Ki into the integral value which is coming here, which is the integral of the error, plus VNIR, which is Kp into the error. So this is Ki into integral of error plus Kp into the error, which is nothing but the Pi value. This is the Pi, which is Vc here. Now the Vc is passed through a limiter. Limiter is another B source. So you see the B source is so powerful. And this V0 is node 5. So that's why I am using 5. V0 is nothing but node 5. This is V0. I have indicated 5. So I will use node 5 here. And output is V voltage. And voltage is, I am going to use a ternary function. What is the ternary function? It is like this. It goes like this. If VNC is this, the limiter output, if this value is less than VEE, V4, what is V4? VEE, which is this. If it is less than that, question mark means then set it at V4, clamp it to V4, else, else, I will check again with 3, that is Vc. If it is greater than Vc, then question mark, set it as V3, that is VCC itself, else, then VNC. This will be passed. So this is the limiting function. What it does is, it will check to see whether it is below this threshold. If it is below, it will clamp to this. Otherwise, goes to the next step, check for the upper threshold. If it is above that, clamps to VCC, or else it will be same as whatever this, it will be passed through. And then dot ends. So this limiting function is actually giving you V0. So this is nothing but of the form x question mark y colon z. What it means is, if x condition is satisfied, then y, send the value y to the output, or else send z to the output. So this is called ternary function, very powerful function which can be used in ngSpice or spice simulation. So this will give you the model of an op-amp, a generic model of an op-amp. You can use it anywhere with this kind of a syntax. So let us put this model into operation. Let us put it into our LU devices.lib file and then make the symbol in KiCad and try to link them up. Let us do this. So let me now go to the file folder, the models. So in models, we had earlier created a subcircuit for the power diode, right? So we have that same file .devices.lib. We can use that and then add one more component called the op-amp. Okay. So let me double click on that. So we have the LU devices.lib and we have this diode, right? Diode model. Let me also now add one more component, generic component name. I say this is op-amp, right? So this op-amp is what we need to model, and let us say dot sub circuit. Let me bring in the file that we were working on. So the file that we were working on. Let me adjust the screen size here. Yes. and let me bring this in. Okay, let me put this in quickly. Name of the subcircuit, op amp, and the nodes 1, 2, 3, 4, 5. These are the nodes that we are passing into the subcircuit, and dot ends. This is the last line that should be there. So in between we have to type in all these lines, and let me have one comment line to indicate that this is V plus, V minus, VCC, VEE, and V naught. So these are our node points, and what these input nodes that we are passing becomes clear. So in between, let me type this in just like what we discussed. Let me do this quickly. I will quickly type it and then come back. So now I have typed in the model that we had discussed, 1, 2, 3, 4, 5. So what I have done, I have added two more B sources here. One voltage which is proportional to this, V plus, another voltage proportional to 2, that is V minus, and then I am having this V error just like what we discussed here, which is V plus minus V minus. That will give the error voltage. Then there is a current source which is defined as proportional to error, and that current source is passed through a capacitance which will give you an integral of that and therefore an integral of the error component. Likewise, I will have another current source proportional to the error and then pass it through a resistance component having some value of resistance, which will give you Kp into E. I am going to give a gain block here, a voltage which is having a value of 10, which is gain 10, and I will use one more B source between two terminals, and the voltage is actually given by this equation, that is the integral part into gain Ki plus Kp into E, which is coming from here. So this will be the output of the PI controller. Then I pass it through a limiter between 5 and 0 output, and I use this ternary function to function as a limiter, and this gives you the function of an op amp. And this op amp model, I will call it in a symbol that I will make, and I will link it up so that you can use it for all future schematics wherever you want to use an op amp, just like another custom symbol of yours. So let us do that. So what I will do, I will go into the KiCad Pro. So when you double click on KiCad Pro, you get this. You have to go to the symbol editor. Go to the symbol editor, and so it will open the symbol editor. Let me maximize that. Important thing, you see I have my components library in place at the top. Now if I go inside, you see the diode power, right? And I can incorporate a new library, or I can copy a old library and then a old component and paste it there itself. But I am going to take a new symbol, and I will say this is op amp, and the default designator X. Op amp is a subcircuit. I'm going to take that as the designator, and okay, so this is what it starts with. I'll keep it to a side. I can, as I told you, I can give any designator. Because it's a subcircuit, it will always prefix with X. So I could also say as O for op-amp. Just like that. It will prefix it with X. I'll make it O1. Or most of the op-amps are coming off as ICs. So you can say that it is U1, so that it is an IC, and there are several such op-amps, and it will prefix it with X because it knows that it is a sub-circuit. Now let me draw the schematic. So what I will do is I will take this and draw this sub-circuit. And important thing, like I mentioned before, let me now draw this like that and this way. Yes, important thing is go to the preferences and grids and see that it is set at 50 mils. Okay, that is very important. And let me take the pins. So I will call all as passive pins. So pin number 1. So pin 1 is V plus. So that is here. Then pin number 2. This pin name is V minus. Right, like that. Okay, I think I made a error here, mistake. This is pin name V plus and pin number 1. Yeah, be careful that. Then let me have another pin. This is pin 3, VCC, and this is pin 3. Right, and I will rotate it and place it here. And I'll take one more. This is pin name is VEE 4, pin 4, and let me rotate that and place it here. Then one more pin, the last pin, which is V0, and this is pin number 5. And let me rotate that and place it here. So you have the symbol of the op-amp in place. Let me now add the plus and the minus signs here to indicate the terminals. I will use this text, add text icon. I will type in plus and then place the plus sign here. Then I will take again the text box and type in minus and place the minus sign here. So now our symbol is ready. We need to do the linking with the sub-circuit model that we have defined for the op-amp. Let me open the symbol properties. Click on that. So you have the symbol properties open. I will say the value as op-amp, because op-amp is the name that we have given in the sub-circuit model. Then go down to the edit simulation model button. Click on that. So here we have to choose the file where we have typed in the op-amp sub-circuit model. So go into models, ludevices.library, open. So here you see that automatically the two models, there are only two models in the lu devices.lib for now. One was the diode power which we used earlier, and this is the op amp. So let me click on that op amp and see the pin assignments that V plus is assigned to 1, V minus to 2, VCC to 3, VE to 4, V naught to 5. This is all right, and you can click OK. You can see here that automatically the sim library path is shown, the sim name, op amp, sim devices, sub-circuit, pin assignments, all those things. Now I don't want to show the pin number in the schematic. I don't want to show the pin name, and all this I am going to make hiding. Now click OK. So you will see all this jumbled up in one location. What you have to do is disentangle them. Disentangle these. This will not reflect in the circuit. This will not reflect in the circuit because we have hidden them. So this becomes the sub-circuit, and we save. Save. So op amp is saved. So diode power and op amp are the two symbols that we right now have. Op amp symbol is linked to lu devices.lib. Remember that all these need to be gray shaded in order that they don't get seen in the schematic. Let me just check to see that these need to be hidden. These need to be hidden. Okay, so now they are all hidden and they are gray shaded and they will not be visible in the schematic. Now you save that. The schematic is saved. Now let us go to the schematic and call this symbol onto a schematic page. So in the schematic, so this is the schematic of the full wave rectifier, but I am not going to use this. I only want a schematic page, any arbitrary schematic page where I can use, use the symbol, add symbol icon. I will use this add symbol icon, and you will see that in my components library, my custom component library, there are now two components available: diode power, power diode, and the op amp. Op amp is the one which we now added latest. So if I click on that, this is the symbol that pops up. Click OK and place the symbol in the schematic. If I zoom in, you will see that this symbol has all 5 pins, plus, minus, and U1. All other things are hidden. Now this symbol will automatically link to the lu devices.lib file where we have the model of the op amp, and it will use that to execute when the netlist is called in the ngSpice simulation engine. Later on, we will use a circuit. We will do a circuit where we will use the op amp symbol. We'll call the op amp symbol and then use it for simulation.